So to see to start the production, let's imagine this case. Okay, it's a dry gas reservoir that is really very uniform, that you can represent with a material balance. You can assume that everything has a uniform reservoir pressure. Uniform reservoir pressure. And moreover, we can say that the wells are all standalone. That means that they are not connected anyway between them. They are producing almost independently. If you say that's a reservoir of gas, we have one well, and that is producing almost to its own separator. Then you have another well from the same producing to its own separator. Okay, and you have a finite number of wells. You have certain n wells. N wells. And also, another assumption that we are going to make is that all wells are identical. And you say, okay, you are putting all of these, and that already sounds very unrealistic, right? The thing is that in early stages of design, we really actually don't have much of that information. We don't know how, we know the wells are going to be different, but we don't know how different they are going to be. So a very good assumption that we can make to start with is to say every well is going to be the same. Yeah. Then we can lift that assumption, but at early stage we can assume. So every well has its own PR, its own IPR and TPR are the same. So now I'm going to ask you, we saw and say the wells are the configuration, it's more or less like that. And here is very close to the separator. So I'm going to ask you, the maximum flow that well, what we call also the potential, okay, that the well can produce, depends on what? If it's open choke.
Separator pressure.
Separator pressure, and that we assume it remains constant, okay, for the life of the field, but also about for something else. Huh? Tubing diameter, okay, let's put that plot here. We have an intersection, right, of that, between that. That's TPR, if we take the equilibrium point at the bottom hole, and IPR, right? But this IPR, in this equation, if you remember the equation, QG equal to CR PR squared minus PWF squared to the power of N. What is the thing that is changing with depletion? Reservoir pressure, right? So we can say that that IPR will change like that when reservoir pressure goes down, right? Yes? So I can say also that the intersection rate will go down with reservoir pressure. The maximum rate from the well will go down with reservoir pressure. Yes, so if we make it in a plot, we're going to call that maximum rate, let's call it for now Q max from the well. Okay, we are not talking on a field scale yet, but we are going to say reservoir pressure, we have a value initially, that's where the rate will be very high, but then when the rate starts declining, when the pressure starts declining, that rate is going to be less and less and less and less. All of you agree? Yeah, that's initial reservoir pressure. We don't know exactly how the behavior is going to be. Might be something like this, might be something like this, but we know it's going to decline. That's the thing that we know for sure. Okay, but now I'm going to ask you also, this PR, according to, we can assume that everything is uniform, is one single container, is one single tank. What it depends of PR? According to material balance, PR is a function of, we saw it just 1 week ago, so how much material I have taken from the reservoir, right? And how do we call that in petroleum engineering nomenclature? It's a function of cumulative production, okay? GP, in this case because it's gas. GP is equal to the integral between 0 and time. Okay, let's say we say the reservoir pressure at a given time is equal to Q gas dt, right? Yes? So, and how is the relationship between GP? How is the relationship between PR and GP? If I haven't taken anything from the reservoir, it's 0. What will be PR? Initial reservoir pressure, right? Yeah. Then I'm taking material out and out and out, so that's going to look declining, right? Yeah. And that depends on the mechanism, what kind of mechanism. If I have, for example, an aquifer, it won't decline so dramatically. It might decline maybe even like something like this, okay? But we are not going to talk about it. What we know is if we start taking out, then it's going to go down, okay? Now I'm going to ask you, this Q max, can I plot it versus GP? Is it possible to make that plot? Or how is it going to look like? Okay, let's try to make it. Here we said 0 GP, we will have initial reservoir pressure. The Q max is going to be highest, right? It will be exactly in this point. So I'm going to put that point here. Now, for if I start taking material out, reservoir pressure is going to go down. Then if it goes down, then also the maximum rate has to go down. Okay? So I'm going to obtain also one behavior like that. Yes? So I'm going to call this curve I mean, does that make sense to you or not? It means depending how much I have produced, I can define the maximum rate that my well can produce. Because this is connected to reservoir pressure, right? Just because of that simple reason. And that line is just open choke. If you remember how I calculated that line, I peak reservoir pressure, calculate IPR, have a TPR, make the intersection. That's how much the maximum that you can produce with your system. I can produce less, that's correct. But that's the maximum that I can produce. So we are going to call that's Qmax, remember, per well. Production potential curve. Now I'm going to ask you, in our field that is very simplified, all identical wells, a big tank, what will be the production potential of the field? If all of them are identical, initial reservoir pressure, I just have to multiply that times n, right?
Yeah.
The number of wells. Yeah. So I just say Q max per well times the number of wells. That's going to give me the production potential that I'm going to call Q field production potential. And here I'm going to say this is QPP production potential. Of GP. So now I'm going to ask you something a bit tricky. How do I calculate this GP? Does it depend on a field, depend on the well production, or it depends on the field production?
Field.
On the field production, right? So this GP is all the time calculated with the field. Okay, and let's say the curve for dry gas, and that's the actual shape. It looks more or less like a straight line. So okay, so you say we understood what is production potential, but why is it so? Why are you talking about it? When, for example, if I have a plateau rate, okay, let's say that is here. That's my plateau rate I want to produce from the field. Okay. If you remember what you had, so how do you find the end of the plateau? What is the procedure you have seen so far?
When it's full open choke?
No. Remember, plateau, I'm choking all the time, right?
Yeah.
So what you do until now to find plateau length, so what you do, you perform a stepwise calculation, right? A stepwise calculation in time, right? That's what we have done in the last class. We have time, a column time 2, time 3, time 4, okay? Then you say calculate Q open choke, yes? And the Q that I want to produce, and I say if Q open choke is greater than the Q that I want to produce, then I'm happy and I'm in plateau, right? If not, I have to use the open choke rate, right? And then you have to perform time-wise calculation. Now, if I tell you, okay, do it now for another rate, do it now for another rate, do it now for another rate, it will be a lot of time-consuming computations, right? But now, how we can use that potential to find exactly the length of the plateau? Let's see. If you have that plateau rate, what is the x-axis telling you for that point? That point here. Okay, it's going to tell you the cumulative production at which the potential is exactly equal to the plateau rate, right? GP star is the cumulative production at which the Q field production potential is exactly equal to Q plateau. Yes? All of you agree? So what happens before that for all the values below? The Q potential is all the time higher than the plateau that I want, right? So I should be able to produce for all of these GPs previous. But for all of the next GPs, I won't be able to produce that plateau rate, right? Now, the time, the duration of the plateau, I can say that is, how do I calculate?
GP star.
Okay, GP star divided by Q plateau. But I'm missing some units, right? I have to multiply times number of days in the year, right? And that's how I find the end of the plateau. Okay? Exactly when I try to find the cumulative production at which my plateau rate is equal to the potential. If you could have done it with these other two plots, right? You could have said for which reservoir pressure I reach the plateau rate, right? And then I have to come to this plot and I say for that reservoir pressure give me the GP, and I can do exactly the same thing. The powerful part of the potential is that I can do that in the same plot. Okay?
Is it necessary to report the plateau period in terms of years?
The plateau period? Yeah,
Is it necessary?
yeah, well, depends on how long is your plateau. If your plateau for gas, for example, you might have to do it in years. But if it's for oil, some fields have just 1 year, so you can report it in months. Okay, or you can report it in days. It depends really on the length of the plateau. What? Okay, so now I'm going to ask you another question. What will happen after that point? After that point, I have open choke, right? And if I'm in open choke, it means that I'm producing all the time at the potential. Yeah? Okay, let's make one example where we derive. So the example is called deriving the a production profile using the flow potential, the production potential, okay, and I'm going to assume always open choke. So the first equation, it's for dry gas, okay? For dry gas, the potential of the field is equal to linear, okay? Just using the same expression that we have here, that is a straight line. So it's equal to a QPPO, that will be the intersection on that point, QPPO. That's the potential at the initial reservoir pressure, minus M times GP, right? And you will see, and actually you will have to calculate for one exercise, that actually you say, but that's a very simple equation, linear. Nothing in petroleum is linear, but for that case, it's fairly linear. Okay, it's linear. Then that's one equation that I have. Okay. Then the other equation that I have is that GP is the integral from time 0 to time t of Q of the field, right, times dP times dt. Yes? So that's the other equation I have. Now the third equation is saying that using that statement, I'm always operating at open choke. If I'm always operating at open choke, that means that Q of the field is all the time going to be equal to the Q of the production potential, right? So let's use that, and the way we do it is we put that equation inside. I think that's what I do. Yes, so we say Q of the field, okay, equal to PPO minus M integral 0 to T Q of the field times dt, and I want to clear how much is Q of the field with time. Now I think we derive with respect to time. And we end up with derivative of f, qf, with respect to time equal to minus m qf. Yes? Okay. Now to solve that equation, I make a separation of variables, right? So du qf divided by qf equal to minus m dt. Yes? And then I apply integral both sides from 0 to a time t, and from in 0 the q of the field will have q ppo, right, to the rate q, to the actual rate at that particular time. Okay, the q at that time t. Yes? And that gives me okay, so that gives me ln of qf evaluated in q ppo and qt equal to minus m t minus 0. Okay, and at the end I don't like this ln, so I convert everything to qf equal to q ppo times e minus t. Okay? Yes?
Sorry,
Yes.
what is QPO?
QPPO is the rate, so that's the potential, production potential at time equals 0, or that means at reservoir pressure equal reservoir pressure initial. Yep. So that's, if you see here, that's the power that I had by putting the potential in terms of the rate. That in my equation I just have rate and time. Okay, and I can actually clear the time, the rate, the behavior of the rate versus time. Okay, I'm using those two equations together. That is an expression of rate versus time. That's a rate also that changes with time. So in that way I can clear what will be the profile. And if you see, so that means if I have time and I have here 0, it will go something like that. Okay, with an exponential decline from QPPO all the way to here. Yeah. So I don't want to, but if you remember, we had another set of methods. Okay, we have material balance. If you remember to balance material balance, we are already we are for a break, right? We have reservoir simulator, and we have also something called decline curve analysis. Okay, where I didn't tell you much about the basics of the method, but the thing is that you assume, or you try to find a physical shape or a type shape that the decline follows. If it's, for example, exponential, hyperbolic, or yeah, what other type you have? I forgot. Okay, you try to, but you see now that it came directly from the potential expression. Okay, that you have, if the only considerations, the only conditions are the potential has to be a straight line. Only if then if I'm producing at the potential all the time open choke the profile is going to be exponential, very powerful. Okay, and you see why it came from the equations. Now, can we use that equation for the post-plateau period? When I'm not operating here, I'm using that equation from the beginning all the way to the end. But what happens if I have two periods, one in plateau and one in open choke? Can I use it? What do you think?
Can you use it for after plateau?
Yes.
When
How?
it's open choke?
Yes, but how? A mathematician will look very close at this equation, okay, and will tell you, well, here you're integrating from the beginning, okay. Now just integrate from T plateau, okay? And you take the plateau rate here. That's the starting point, right? So you can use exactly the same equation. The thing is that depends where you integrate it from. Yeah. That clear? Yes? Okay, so equation, let's call it here equation 1, okay? That gives you, equation 1 gives you a decline shape for the rate. And also it can be applied for decline periods, okay, producing an open choke. Using appropriate bounds in the integral. Okay, I have just to take that equation and make the integral really maybe I should put it up here. Yep. Should we take a break? 15 minutes, or you prefer to continue? And we try to finish 10 to 4. Yep. But you have to tell me we are approaching if I don't stop, okay? Stop, end of the class. Because otherwise I'm like your friend, okay, we'll take a bit more time and you're going to be angry later. Yeah. Okay. Now let's see some of the. So what is that m? Okay, what is this decline constant? How can we find it?
The slope.
Huh? The slope, okay. But the slope, where does it come from?
The straight line curve.
Okay, I will have to calculate it, right? I will have to calculate or approximate that potential somehow. Okay, so now I'm going to ask you, if you have already run one case like that, okay, using a stepwise where you each time you go, can you just find the potential from there? And can you use it for another plateau rate? Okay, let's okay, you're doing that time wise. Okay, so let's take that. Well, let's make it from scratch, okay? So you have, remember, you have time t1, t2, t3, t4, etc. Then you have what did we have? Cumulative production. Okay, so we had GP initially was 0. Then we had a reservoir pressure, initially was PR initial. Then what else did we have? We had a rate also from the field. And we had a bottom hole pressure. Sorry. By the way, bottom hole pressure, if you see many software in the field, etc., instead of writing PWF, it's going to be BHP, bottom hole pressure, everything in capital. We don't use it here, it's not SP nomenclature, but that's how you will see it. Okay, so here you have P available. Okay, that will be calculated co-current with IPR. And then you have PWF required, calculated counter current with TPR, right? What else do you have? P separator, of course, and at the end the final rate of the field. Okay, this will be the open choke, and that will be just the Q that I'm actually going to produce, right? And here I have someplace up here, plateau, desired, a desired number. Okay, so what I told you is you assume a rate, right? Calculate counter current IPR to calculate the bottom hole pressure available. Then with the same rate go counter current from the separator to calculate the required, and I want these two to be equal to give me the potential, to calculate the potential. So I use the solver. I have to create, I'm missing here an error cell. That will be PWF minus PWF required minus available, and I might square it. Okay, and I say solver, please change that rate until this error is 0. Right? Clear so far? Yeah. And now what happens? The Q of my field, if Q open choke is greater than Q desired, then I just put Q desired. Else I have to put Q open choke, right? And then on the GP I'm going to say, well, here this will be the previous GP plus the Q of the field. Let's put it maybe Q, it will be equal to that plus Q of the field times T2 minus T1 times the number of days per year. Yeah? Yes? Okay, and you solve the exercise, etc. So now what I want to say is, if you take that column and that column, okay, the potential and the GP, if you take those two columns and you plot them, and then you will obtain the potential, right? You will obtain QPP versus GP 0, and you will obtain that famous potential curve. What I'm going to ask you now is, can you use that if you want to analyze now another plateau rate? Can you use that to run your calculations instead of doing it stepwise? Yes or no? If I want now, for example, I used before Q plateau 1, okay, a number. And now what happens? My supervisor comes and said, what happens if Q plateau is equal to Q plateau 2? Okay, let's say, before we had, let's say 10 million standard cubic meter per day, and now I want 20 million. Now I'm asking you is, can I use that curve to calculate, to do exactly what we have done? Can I come to that curve, find here 20, e to the 6, find the QP star, and then say GP star divided by Q by 20. And that will give me the duration of the plateau. Can I do that?
Yeah.
Yeah?
Yeah.
Why?
Because it was calculated independent of the Q plateau that we.
That's one thing. If the production system doesn't change, the number of wells don't change, the reservoir doesn't change, the anything, the IPR, the TPR, why the potential should change if I'm just changing the rate? Doesn't change, right? So it doesn't matter if I calculate it for one case, I can use that later for all the other cases. And that's what is very beautiful of the potential. And really you don't have to run any more these calculations. Okay? Now, what are some of the problems with applying? So you say, okay, that's a wonderful method. We can use it for design. But what? So what? So why don't we use it? Okay, so why? What are the limitations of the potential method? Okay, so what limitations can you? First, there might be changes in the production system. That means you can change the number of wells, for example. Okay. And these changes are made at one particular date. Okay, and these changes are applied at a particular day. Okay. So for example, you have your production for a certain time declining, and then here you decide to drill one well, and then the production increases, and that's at the given time. We work on a project with time. We don't work with cumulative production. Maybe from this example we should work with cumulative production. Okay, make things much easier. We take time out of the equation. But when we make operations, really we say here I'm going to install, for example, a compressor. Here I'm going to lower separator pressure. Here I'm going to add one more well. And what happens then? The potential at that point will change, right? So one way will be, or how it will look like if we put it QPP versus GP. Okay, initially it was a straight line. And when I introduce, at that particular time, I had produced one particular GP. Let's call it GP double star. Okay, it will have a jump, and it will continue with the same decline. Yeah. So that's what one of the inconveniences. If I have a change in the production system, then I have to convert from time to GP, and that's kind of not simple all the time. Okay. What is the other? What could be another limitation? If you think one of the assumptions that we are making is that the IPR is a function of reservoir pressure, right? Or a function of cumulative production, right? And now I ask you, is that always like that? Can I say that the IPR that I'm getting from the well is just a function of cumulative production? Okay, why not? The one that is awake, why not? Huh? Yeah, let's leave injection for one moment. But you say if it's only let's say imagine that you have a horizontal well, okay? And you have the oil layer and you have the gas layer. One of the main issues with horizontal wells is that if you lower the pressure in the wellbore to a critical value, you will have coning, right? Yes, so you have to be all the time be careful that PWF is higher than this critical pressure, as we call critical coning pressure. Okay. What will happen if you, for example, for some reason you went below, you will have coning, and then if you have coning, the IPR will change. Okay, and in that case, it won't be anymore a function of, for example, of cumulative production. It just at some point it changed just because the pressure went down. So in that case, I cannot say that the IPR is just a function of here missing the units, PWF and Q. It's not a function of cumulative production. Okay, but it's a concept. So we are going to have an exercise, maybe in class next week, or if not, I will put it for the homework. But already the homework is having maybe too many, so I have to do one here. But you will see, try to use this potential concept to design a field. And it's a very nice exercise about blending, when you have blending and you have two oil fields. Yes, that clear? Yeah. Well, let's before, let's say, take an example with two reservoirs. Okay, let's assume that I have reservoir A and it's producing separately to the processing facilities. And I have a reservoir B producing also independently to the processing facilities. I plot the production potential of field 1, okay, or field A, versus, and here I have to be careful. I have to use here the GP of field A, right? And here I plot also Q production potential of the field B versus GP of B, and I have those two values. Okay. And let's say I'm producing and I'm committed here to get a Q plateau of certain amount. Okay, let's say it's an oil reservoir, so we are not going to use it in G, but it will be N because it's oil. And I want a certain plateau of 100,000 barrels, for example. Yeah. How do I decide how much I want to drain from each reservoir? What will be, if you think about it, what do I want? How much do I drain? What will be the Q plateau of B and the Q plateau of A? Okay, that's the question. How do I define those rates? What will be a nice way to define those rates?
Many options.
Many options, okay. But let's say you want the length of the plateau to be as long as possible, right? But so then that, what implies that? That if you're producing the other two also at a constant rate, that means that they have to finish exactly at the same point. Oh, okay, the T plateau. So let's say if I want to maximize, if T plateau of the field is to be maximized, then T plateau A should be equal to T plateau B, right? Simple as that. Because I don't want one to stop before the other. I want the two of them to stop exactly at the same time. Yep. So how do I do that? Yeah.
You run them at different rates.
Yes.
Can you?
You? Yeah, let's say
One runs them at different rates.
if I don't know, I assume, right? Yes. So one procedure, I'm going to tell you here the iterative procedure, and then we might have some clever mathematician. Okay. I say Q assume, I'm going to remember, just like solver. I assume Q of the plateau of A. Yes? Now I can calculate Q plateau from B. That will be just this 100,000, okay, Q plateau. Too many O. 100,000 minus Q plateau A, right? And then I can go to each corresponding plot. Let's call it just QP. Well, it's going to be confused, but QPA and QPLB, and I can get the NP star B and the NP star A, right? And with those numbers, we already know how to calculate the duration of the plateau. Yes? So I go to potential plot, the production potential curve. Okay, and read NP star A and NP star B, and calculate T plateau A and T plateau B. Okay, that you know already how you calculate. It's NP star A divided by Q plateau A, okay, and times the number of days per year. And then you ask the question, is T, and here I'm going to make a trick, is T plateau A equal to T plateau B? If not, what do I do? Go back and assume another rate for field A. Yes? If yes, that is the final solution. Okay, the Q plateau A, Q plateau B is the optimum solution. Yep.
Is it not? We assume like higher rate or lower?
Yeah. What do you, if for example,
If is it not, we will assume again.
okay, you will assume again, but so if for example that one is higher than this one, what do you have to make? That means that I'm depleting A much quicker, yes, and that's not what I want. So I have to reduce the rate of A and increase the rate of B. Yeah. But remember, we can use solver for that. We can do it also if there is a mathematician with us. We can do also make it into a system of equations, okay, and we can solve it. But I think I have done it someplace, but I think that will take, I will just paste it after class, okay. But you can find analytically what will be the intersection between them. If you have this like an equation, keep PP equal to keep PPO minus M, that's a very unfortunate name for Q potential, and P. Okay. If you assume that equation, then you can find exactly the intersection. That here? Yep. Now I'm going to ask you, what happens if I decide not to produce them in constant plateau, in constant rate, each one of them? Can I still find can I still maximize plateau? No. Well, we'll leave that question for the exam. Okay. Clear about potential? Yeah, we will do an exercise on Tuesday, hopefully, about potential and about the previous part, and you will get it also at least one exercise in the set that comes. Limited because of some things, okay? Because first, you not always can make that assumption, okay? Because you have many wells. Actually, assuming a big container is not that everything has a uniform reservoir pressure is not, sometimes it's not exactly a good assumption, okay? Why? Because you have a very aerial difference, and actually in that case you can say in big reservoirs the potential of the well is not a function of the NP of the field, okay, or the GP of the field, but QPP of the well is actually a function of the NP of the well. Okay? Just because there is so many heterogeneity that each well can almost behave like an independent reservoir, okay, and it will have its own potential depending on how much you have produced from that well, okay? And then it becomes please note here that I cannot really make a potential for both fields, okay? I have to keep track for each one of them separately. I cannot make that curve for both of them, okay? Because you have, each one is the production, what you have produced from B and what you have produced from A. Okay, let's have a short discussion before, I know now it's already 10 minutes to go. So let's talk about one last thing. Let's go here. Okay, now we are covering a very heavy block that implies a lot of technology and knowledge. That is reservoir depletion, production potential, production scheduling, flow equilibrium, choking and boosting. And then the last part is what happens surface and downhole production networks. Okay, you already know how to make calculations in a simple system, single well system. But now we have to see what happens with networks. So what are production networks? Production networks is arrangement where I collect the production, I commingle the production of all individual wells in a network of pipes or in a system of pipes that will take it all the way to the processing facilities. Okay, collection. So that's what I call collection or a system of pipes. It's better to call it a system of pipes or flow lines that commingle the production from the individual wells and take it to the processing facilities. And you have, for example, you have well 1, 2, 3, 1, 2, 3. Usually, if you are subsea, there maybe try to drill them in clusters so they will be close enough. So you try to make all of them together in a manifold. These 3 together also in a manifold. These 3 together in a manifold. And then you have some flow lines that will take it further to the facility. Okay. So especially relevant networks for subsea wells. And I think here I have some nice pictures. So let's see. We have to put some color to these slides. Here. Okay, so that's a network. We can take that figure. So in that case, networks really make very difficult this concept of available and required, right? Because we said, okay, here I can calculate available, but here required, I have the separator, but I have to go back here and here and here and here, and then the rates are different. This is handling the rate of one well, this is handling the well of several wells. So how do I do equilibrium in that system? So some examples are of networks. Okay, so are in this case an onshore field, not only happens offshore, but an onshore field, the Salim field in Russia. Anybody coming from that area here? No? No Russians? So you have the wells are located in clusters, and then they are commingled. All of their production is commingled through flow lines, pipelines, until some place where you have the processing facilities. Then I think I have some other nice pictures. That's Gulfax. What I call subsea is particularly important when you go to subsea wells where you have several templates, where you have wells, you commingle the production from them, and then you send it further to the platform. Okay, also the same thing here. The main thing about networks is that there is interdependence. In networks, there is interdependence between wells. Okay, there is interference between wells. That means if you have, for example, one well here, and then you join it with another well here. Let's say that well has a very big IPR, has a very high CPR minus, or has a very high reservoir pressure. Then it will exert some kind of a back pressure due to the high volume that it's producing. It will exert some kind of a back pressure on that well. So the production of that well will only depend on the separator pressure here, but it will also depend on how much that well is producing. Okay? And then the system becomes more and more complicated. Some other example in the Amazonas, in the largest rainforest in the world, I think, if they haven't cut so many trees this year. So it's in that location, and in that case you also have the reservoir is relatively spread. So what they did is they make, maybe I have some other picture later. Okay, make a hole in the forest. From there you drill your wells, and then you connect them with some flow lines, and you take it further to the processing facilities. Okay, and you need to have, in that case, they take the production from the river in boats, okay, in tankers. Some other examples. So that's, I think, the processing plant in Urucu. That's called the Urucu field. If you want to Google it and join Greenpeace or something. Okay, Gulfax. That's the Salim field in Russia. And I think we have some other that in Colombia. Okay, we have networks, and they are, when in the North Sea, using subsea systems is becoming more and more common, and also some onshore fields that are remote, in remote areas, they are also becoming more and more common. That field, I think that's just the map, but the field, okay, again, you make in the savannah, the field is someplace here, okay, the Rubiales field. We were working a bit with it. The same thing, you have a big network. I think that actually is the picture of one of the networks. and they have different name. They call trunk line. And even you can have it in any environment, also in the desert. That's not that's something else. Okay, in the desert where you have, let's see if I remember correctly. You have dunes, and then you have some part where you have a flat part. That these are called sabha. Yes, sabha. How do you write it? Like that?
I think
You don't know?
yeah, I think so.
Okay, sabha. That's called a sabha. And then you cannot drill. You have a big reservoir under this sand, and you cannot drill through this. You cannot put anything through the sand because it will get dust. It will disappear. Movement of sand all over the place. So they drill from the sabha where you have a flat area. Then they have to make a tunnel connecting all of these sabha until it reaches to the processing facilities. Okay, and they have actually like machines to make tunnels through the dunes. Okay, this might be, I'm not sure how much, but like 10 meters, 20 meters height. Okay, huge dunes all over the desert. A field located in the border with between Saudi Arabia and the Emirates. A huge networks maybe with 600, 500 wells. So it's you have there, if you have dependence with 2 wells only, imagine when you have 600 wells all producing to the same network. Okay, but we need them to send a line. In that case, imagine if you try to put a line to each one of these wells all the way to the facility, it's going to be very expensive. Maybe it's the best. Okay, maybe you can test the well, you can know the IPR, you can know everything, but first you're going to make the Greenpeace are going to be angry at you because you make so many scars in the rainforest, and then it's going to be too expensive. Yeah. So we have to live with networks. That's the message. Networks are in many places, and we have to live with networks. If we have some of these, so we have to quit now. If we have these dry wellheads that we can drill from the same place, all of them go very close to the same separator, that's fine. Okay, I can use single well equilibrium. But if we have those systems, we have to use something else that we are going to discuss next class. Yep. Okay, before we close, any question? No? Okay, we close. See you next Tuesday.